This is another video for the lecture Intro PDE. In this lecture we present the first part of section 1.5. So we will introduce the method of characteristic. We will finish this method characteristic in the next video. So there are two videos on this section 1.5. Now, what is this section about? We will solve a very general first order partial differential equations. And this differential equation has the following form. We have some function f. And this function f is defined on an open subset W of Rn cross R cross Rn. So our unknown function u, u is the unknown function. So the unknown function u is defined on an open domain, is a real valued function on an open domain in Rn. Omega we call this domain. So and then the gradient u is of course a function going from u to Rn, so it's a vector field. And x is a vector, so this expression here is now well defined. Also also the gradient u is a vector, this is a number, and this is a vector. Okay, so this is our general form of this differential equation, and we will make some assumptions on the function f. It should be, I think finally we assume that it's 3 times differentiable. And then we will construct a solution. So for such a differential equation, such a first order partial differential equation, the method of characteristic applies and gives really a solution. Now, we have already applied twice in simple situations the method of characteristic, namely in the transport equation and in the scalar conservation law. And in both cases we have seen that we construct a trajectory. So we look for a trajectory. So we look for a continuously differentiable path going from some interval, from some interval to omega, interval, some interval to omega. So we look for a trajectory, a suitable trajectory, which goes from an interval to omega. And this we have to choose properly. We will see in a minute how we define it. And then what we do then we define P of s. This is just the gradient u of x of s for a solution, and set of s we define as u of x of s. And so we assume let u be a solution. So we assume we have a solution, and then we choose a proper path. This will be made more precise in a minute. And then so we obtain a path going from we combine this to x of s, set of s, p of s, and now try to describe this curve or this trajectory by an ODE. This is the essential idea. Yeah? We try by an ODE. And of course, we will use this, this equation. Okay, this is now the clue. So this we want to achieve. This means to define an ODE. Yeah, this function p has of course components. Let's call p of s one component. And now we want to calculate. We want to determine the derivative. Okay. Let's calculate this derivative if it's a solution. Yeah, so it's d by ds of du of x of s by dxi, because p we define as the gradient, so the ith component is just this expression. So we get a second derivative. Yeah, so we get a second derivative. Now this for this we have to apply the chain rule. Yeah, the inner function is x and the outer function is u. So what we get by the chain rule is of course exactly this sum here. Yeah, we have to take here the derivative with respect to some xj and then xj by ds. Yeah, so the second derivative gives this expression. Now, of course, we want to use this equation. Yeah, and if this equation is true, then of course also all derivatives vanish. Yeah, this equation should be true for all x. So all derivatives should vanish. Yeah, so this should mean d by dxi of f of gradient u of x, comma u of x, comma x. This should be 0. Now we do the calculation by again by the chain rule. Yeah, yeah. We have an inner function x going to du of x, u of x, and x, and an outer function which is f. So we apply the whole chain rule. So we first have to take partial derivatives with respect to this expression, and then the inner derivative is in this time a second derivative. Yeah, because the gradient u is already a first derivative, and if we differentiate this again, we obtain the second derivative. Yeah, by the second derivative, the inner derivative is the j here, the same symbol as this, over which we take the sum, and the second partial derivative is with respect to dxi. Yeah, so this is if we take the derivative at this place with respect to xi. Now to take this at this place, the derivative with respect to I, because u we call set. U we call set, no? The second variable we call set. Yeah, we write for f. Yeah, we write for f. We write just f of p, set, and x. Yeah, this is our convention. So this is partial derivatives here with the first variable with respect to p. Now in the second place we have partial derivative with respect to set, and then the inner function is u, differentiating with x we get this, and here we just have this partial derivatives. Okay, so this is 0. Now look at this equation here. Yeah, here this equation here. Yeah, we have such a second derivative. Here we also have such a second derivative. They are not completely the same because the orders are different. But if u is twice differentiable, so we assume u is twice differentiable. Very important, because then we know second partial derivatives commute. Yeah, so this means second partial derivatives commute. So we know that this expression is the same as this. So to find nice expressions, yeah, now this gives us a hint how to choose this expression, the derivative of the curve. Yeah, we choose it in such a way that this sum is just the same as this sum. Yeah, so this is the idea, and then we hope that everything works out nicely. Okay, so what we do is we fix our curve. So we fix this curve by giving it by fixing the derivative. So we fix the derivative of our trajectory by this formula. Yeah, because then this sum here is equal to this sum. Okay, let's see. What do we obtain? Yeah, then, of course, then we can rewrite this equation here. Yeah, now let's calculate this equation. Yeah, so pi of s, I just take the derivative because this is a function just of one variable. We just denote this as s. Yeah, so this is now this sum, and if we define this expression here as this sum here, then we get this sum, and since this is 0, we get that this is minus this minus this. So we get this is minus df of p of s, z of s, and ux of s divided by dz, sorry, partial z, dz minus the last term, df of, here's missing a bracket, of p of s, z of s, x of s, and now with dxi. Yeah, so this is now this differential equation here. And before we already have chosen this, so we have xj prime of s is equal to df of p of s, z of s, x of s divided by dpj. Yeah, this is this equation. Maybe we now call the indices I. Okay, and finally z prime of s. Now we have to calculate z prime of s, and this is of course d by ds of u of x of s. Yeah, and again we have the chain rule, so this is sum over j equal 1 to n, and then we have du by dxj of x of s, and the inner derivative is just xj prime of s. Now we may insert this and may insert this, yeah, and what do we get? So we get, this is of course the same as sum j equals 1 to n pj of s, and here we have df of p of s, set of s, x of s, and partial derivative with pj. So we have this system of differential equations. Yeah, here we have written it. Yeah? Here's again the calculation. So this is this system here. Yeah, you see this is this equation, and this equation. Now let's look at the system. Yeah, and now the essential clue is this is a system here which is for given f just an ODE without any knowledge of u, of the solution. Yeah, we started with a solution and obtained this ODE, but now we have an ODE, and this ODE makes sense without knowing the solution, the solution u. So this is just an ordinary differential, a system, of course. Yeah, we have n plus 1, also n plus 1. So 2n plus 1 unknown real functions, but an ODE system. Yeah, so this has, and we know by ODE theory that we have, by Picard-Lindelöf, that we have local solutions. So let us summarize our calculations in the following theory. So we have a real differentiable function on an open subset, u a twice differentiable solution on an open subset of our given first order PDE. Then every solution s, x of s, of this ODE, yeah, with the function here set p and s, solves this ODE. So all together we get a solution of this ODE system. Yeah, and now the next step is of course to introduce boundary conditions. Yeah, initial value problem. We know ODE systems have uniquely, so ODE systems have unique solutions of the corresponding initial value problems. So, yeah, if you remember, for the transport equation we fixed just a line for t equals 0, and similar for the scalar conservation law. Now here we do something very similar. We fix our solution, yeah. Now we introduce a boundary, some kind of boundary value problem. Yeah, so what does this mean? Yeah, let's see. Also we have here on our set omega. And now we fix the hyperplane which is orthogonal to the last component. So we fix this hyperplane, yeah, which is orthogonal to the last component, yeah, through some point x0. This equation means that's the hyperplane which is orthogonal here too. And on this hyperplane we fix the value u of epsilon. So we give our values for on this hyperplane for a function g, yeah, and g is our boundary values. Yeah, g gives boundary values. Yeah, okay, boundary values. Maybe this is not so clear why this is a boundary. Maybe it's better to call this Cauchy problem, yeah, because we fix the values on the hyperplane. Yeah? The idea is we fix the values on the hyperplane. Okay, so now we want that the hyperplane has this form, but in general, there might be some systems that we don't know the values on such a flat plane, but on any submanifold, any hyper surface, so any set of one dimension less. Now, what we do in general, a general hyperplane, hypersurface, a general hypersurface can be mapped, yeah, with the implicit function theorem to such a flat plane. By C1 diffeomorphism, or more general diffeomorphism. Yeah, not only C1, we will need more. So by a diffeomorphism. So what does this mean? We have a. So what does this mean? Yeah. The idea is we have here some subset omega, and we have here another subset omega prime. Yeah, and here let's assume that here we have a more general hypersurface, and then we have a map phi such that here it's really a flat hypersurface. Yeah, so general hypersurface, and here we have a flat hypersurface. But this means we have to transform our first order PDE, yeah, transform PDE, the PDE on omega. So this is the idea now, the PDE on omega to PDE on omega prime. Okay, let's do this calculation. Yeah, but this is quite simple. Yeah, because This is just the chain rule. Yeah, functions here, if we have here a function if we have on omega prime a function v, yeah, then the function u is just a composition v composed with phi. If this function here v goes to r, then we can take the composition, and so our function here, our solution should be the composition of a solution of another system here with phi. Okay, then do the chain rule. Yeah, the gradient of this composition is clearly this expression. By the chain rule, we first have to apply the Jacobi matrix of phi of the first map. Yeah, we use the chain rule. Yeah, and then the derivative of the composition is the composition of the derivatives. First the derivative of phi, and then the gradient of v. Yeah, and then in this way we obtain this. Yeah. Here we should note, yeah, if we consider this as a matrix, n by n matrix, then this should be a row vector. This should be a row vector times an n with n entries times n by n matrix is again a row vector. Yeah, so this is the connection. Okay, but this means, of course, if we call y the image, yeah, the elements y here, and here this we call x. So if y is phi of x, then of course x is given by the inverse mapping of applied on epsilon. Okay, so we may express this here as gradient of v at epsilon times phi prime evaluated at this point. Yeah, this should be x, so at this point. Okay, so this means this differential equation is equivalent to this differential equation, yeah, for the solution of v. So, yeah, here we just replaced the derivative u by this expression here, and of course the values should be the same, and x is the inverse of inverse mapping applied to y. So we may transform any first order PDE system, first order PDE of our form. Yeah, so we really solved this problem. We just obtained a new function, yeah, from the function capital F, which describes our PDE here. We obtain a function g which describes our PDE here. Yeah? The function f describes on this side, and the g describes the PDE on this side. Yeah? And they have the same form. Okay, now we may apply okay, now we want to give the initial values. Yeah, we have to give the initial values. And of course, yeah, we need now for our system, yeah, for our first order ODE system. Yeah, moment. Here is our ODE system. So we need all these components on as the initial value, yeah, on the hypersurface. So we need u, we need the gradient, and we need, of course, y. Yeah, so the coordinates, the gradient, and the value of u. The value of u is here given. Now, what is with the gradient? With the gradient, since we now have achieved that this plane is is that this plane is flat, yeah. So we know that the components, yeah, we call the initial values along the flat hyperplane are denoted by G. We have G as the value, so Q stands for the derivative. This is gradient U of y. Yeah, G of y, this stands for the values. Yeah, and y of course stands for the coordinate. So we need to give this. Yeah, this we have given, this we have given. Now we have to give this values. Yeah, so we need this values. Yeah, since the hyperplane, yeah, the hyperplane has this form here. This is the hyperplane. So it's orthogonal to the last component. Yeah, so epsilon is just a vector. Epsilon 1, epsilon n minus 1. Only the last vector is fixed. Yeah, epsilon n plus 1 is, no, sorry, not n plus 1, but n is fixed. Yeah, but this means the first n minus 1 partial derivatives of u, they are given. Yeah? So these components, these are given. So we have qi is equal to dg by dye for I equals 1 to n. So this means there's only one missing, yeah? Only qn. But of course we want to fulfill the differential equation. So we need to obey q of epsilon, g of epsilon, and epsilon. This has to be 0. Yeah, this has to be 0. So this is an extra condition. Yeah, this is one extra condition for one real function. And then we can apply implicit function theory. Yeah, by the implicit function theorem, this equation uniquely determines function q of n locally, so nearby our one point, nearby we choose one point, yeah, and so how we want to call this point, yeah, here we want to call this point P0 x U0. Moment, we call this P0 Z0, of course, x0 in W. Yeah, with, of course, this has to be a point where our equation is fulfilled. X0 is equal to 0. Okay, so we assume we have given such a point, and then by the implicit function theory we know that this uniquely determines this one real function Qn if this derivative does not vanish. This is an easy application of the implicit function theorem, because we have one equation for one real variable. This is differentiable. Now, if the derivative by this variable doesn't vanish at one point, then in the neighborhood of this point, this equation implicitly defines our real function. And in this way, we then obtain this lemma. Okay, so what we this means we now know that by the implicit function theorem we have the following theorem, which says the following: we have f on W continuously differentiable. We have one point here on this hyperplane, and we have given our function g on this hyperplane, real function, this initial value. And then what we want is we want on this hyperplane all initial values. So we want the function q, the function g, and of course the coordinate. The function g and the coordinates are given, so it remains to determine function q. The first n-1 components of q, because q should be the gradient of u, are just these derivatives. So they are also given. So it remains only to define Qn. And Qn is, by this equation, uniquely determined in the neighborhood of this point by the implicit function theory. So this is the proof of this lemma. And then in the next lecture we will show that under these conditions we indeed obtain locally a solution of our PDE, first order PDE. So this is what we do today. Let's recall what we have done today. So what we have done is we introduced our first order PDE here, this PDE on one real function, first order PDE of a very general form. Then we assume that we have given a solution, a differentiable solution, and then we were able to find an ODE system. Given any solution, we find this ODE system. So this ODE system, and this has the great advantage, it doesn't depend on the solution at all. So if we have corresponding initial values, we can locally solve this ODE system. So for any solution, we obtain this ODE system. And then in the second step, we wanted now to introduce initial conditions. And this means, to recall this, we wanted to have the initial conditions like general hypersurfaces. But general hypersurfaces we can usually transform by diffeomorphisms into flat hypersurfaces. If nearby by some point, if they are really submanifolds. So this hypersurface we can make flat by a C1 diffeomorphism. So we thought about how the PDE system transforms under this map. And this was an easy calculation. We found that we can transform this PDE system into the PDE system F here defines our PDE system G here. Yeah? So we can just transform our PDE system of first order to another PDE system of the same form, also of first order, and we achieve in this way that our general hypersurface becomes flat. Okay, so then we have now a flat hypersurface, and then in the last thing we determine the initial values. Yeah, and for this we need two assumptions. We need first that around one point, which should belong to the zero set, yeah, to the solution of set of our PDE system, and we need this condition in order to obtain the unknown function Qn. Yeah, so but this is a rather mild, rather weak assumption. Yeah, only these two numbers. Also this should be 0. Of course, this has to be the case because we are looking for solutions. And this is just a weak assumption that this derivative doesn't vanish. We will see that this will play some role. And then we will see in the next section that we indeed can solve nearby this point the first order PDE. Thank you.